about capacitance. So we need to calculate the capacitance with different geometric shape, and capacitance in parallel and series, very simple. So I suppose you learn it very well in circuit analysis. Energy store, still very simple. And actually, we'll cover capacitor with a dielectric. So we'll rewrite the Gauss law in another form. It is quite similar. So for a capacitor, it consists of two isolated conductors. So for this one is two plates with charge, positive Q and negative Q. So the capacitance is defined from the charge equals the capacitance times the voltage across it. So actually, the voltage may comes from a battery. So suppose we may have a so you may have a battery here and connect. So we have a potential V, and we have charge Q on both plates. The top one has plus Q, the bottom one has negative Q charge. So the C is Q over V, of course. And actually, the C is related to the dimension of the plate and the distance between them. Also, the material between these two plates. And we'll talk more about it later in this chapter. So actually, it's worth noticing that between the two plates, the electric field is approximately uniform. The direction is from top to bottom, from the positive side to the negative side, which is roughly uniform in this area. But outside this area, it will something like this. And actually, we'll call this the fringe E field, fringing, this word. So it's not uniform anymore. So actually, say when circuit with a battery, an open circuit, there's a switch there, and a charge capacitor is complete by closing the switch. So just switch it. So you will be familiar with this notation when you study the circuit analysis. So it's closed when t equals 0 or t equals to t0, something like that. So when the switch is closed, the charge will go to this plate and this plate. So this will have positive Q, this will have negative Q. And nothing special, I think. So what we concern is about the electric field. As I mentioned, this part will have a uniform E field, so we use the Gauss law to calculate like this. So for this part, you will have something uniform E field throwing out this Gaussian surface. This red dot is, maybe I can zoom in. Okay. So this red box is the Gaussian surface. So for the upper part, there will be no E field in the conductor. So no flux for the top surface, and for the side, the two sides, there are no or relatively small E field flowing out or flowing in the Gaussian surface. So the only flux is contributed by the bottom side, which is E times the area. Okay. So actually, we have learned this formula in the previous chapter. The voltage difference is the negative line integral of the E field. So we can also calculate this line integral is calculated from I to F, and we define I is here and F is here. So actually the path is in opposite direction from the E field. So actually, if we know this is negative, this is I, this is positive F. So we merge this minus I with this integral. So the lower and upper bound are reversed due to the negative sign. And V is the voltage between this plate and this plate. Any questions up to now? Any questions? Okay, up to now, very easy. So as I mentioned, the flux is only contributed by here, so which is nothing but E times the area. Although it is cross sections, but actually it's a 3D graph. Actually, it should be something like this. So the area is A. So we have the Gauss law to be simplified like this, and actually as a E field is uniform, so this line integral is nothing but E times D. D is the distance between these two plates, so V equals VD. Very simple, and E of course equal to V over D, and we substitute E into this equation, you get this one, and also Q equals to CV, as I mentioned in the very first beginning. So V can be cancelled on both sides. So the rest of the stuff will be simply like this. C equals epsilon 0 times A over D. So actually, the capacitance of parallel plate capacitor is proportional to the area. So if you need a large capacitor, then the area should be large also. And or you can make the distance between two plates very small, which means the two plates are very close to each other, but they cannot touch each other. Otherwise, it's just a conductor, not a capacitor. So very simple, I think, high school issue. Okay. So the next one, cylindrical capacitor. So actually, this is a cylindrical, but also, although it is draw something like two circles, it should be something like this. Maybe I use another color. So the outer one would be something like this. Something like, maybe like this. well, something like this. So the cylindrical. So the inner cylindrical is this part. This part. And the outer one is this part. So in the cross section, a cylindrical capacitor of length L. So actually the length is this part. The length is this part. And it assumes the two coaxial cylinder of radii A and B. So this is A. So the small radius is A, the large radius is B. And we concern the E field at radius R, roughly between the two cylinders. And actually, we also assume that the height is much smaller than the radius. So it should be a tall cylinder. Maybe if you have disassemble your computer, you can see some capacitor like that. It can be exploded if you reverse the positive and negative side. I'm not really sure you have see that kind of capacitor. Well, if there's still some time left, I can show you on the internet. So for the Gaussian surface, this red circle. So also the E field is uniform within these two cylinders, so that for the Gauss law, the left side is just epsilon 0 times EA, and A will be this circle 2 pi r times the height, the total area of the side area, exclude the top and bottom because all the E field are on radial direction, so there are no E field going up or down. So the only thrust contributed by the side surface, so which is epsilon 0 E 2 pi RL. And actually we have this V equals integral for EBS. And actually we substitute E equals Q over 2 pi epsilon 0 L. And R is inside the integral because ds is in radial direction. So ds is actually the same as dr. S is equal to R, I mean. So for this integration, it is something like this. So actually, we have a higher potential at the inner cylinder and lowest potential at the outer cylinder, like this. 为什么呢？因为它是对称的，对称。Because it's assumed that L is much larger than B, so for different heights, it's assumed that all the E fields are the same, contributed by the same part. Is something difficult to draw. But actually, we make this assumption for this case. Actually, it's something like this. The green one is supposed to the inner cylinder, and the red one is the outer one. So actually, all the E field would be on radial direction, something like this. And we assume that L is very large compared to B. This is B. This is A. This is A, and we assume L is much larger than B. So actually, for different height, we also assume the E field is uniform in the cylindrical coordinate. This is facing this way, this is facing that way, but for the cylindrical coordinate, they are the same. Or you can think that E dot dA is constant. So we substitute this part into here. Okay, I think, well, so there's some tricky stuff here. Here is a minus sign. Here is a minus sign. So why we have this minus sign? Actually, the minus part should be here. So it is C. The positive is here. So A, but how this minus I come from? Actually, when we talk about the integral from minus to positive, which means that ds should be this is the direction of ds from the negative to positive side. And actually, for cylindrical coordinate, R should be from inside to outside. So in this case, dr should be dr should be equal to minus ds. So we have a minus sign here. So we have minus sign here. So this integration is easy, just log out, and we have a negative sign, so it's nothing but log b over a, because log b minus log a, so this is log b over a, and like this. So finally, we have Q, we have V. So we divide V to the bottom, or I should say, divide V on both sides, divide V on both sides, and then we put all the other stuff to the left side. So it will become this, because Q over V is C. So we can get this equation. So any questions? Okay. So for this one, spherical. This one will not divide it, but actually I think it is possible for you to divide it yourself. So actually for this case, although the cross section is the same, but for this case, the inner one is a smaller sphere, the outer one is a larger sphere. So they are two spheres with a common central. So they are not cylinder anymore. They are not cylinders anymore. They are two spherical with the same center. So the capacitance between them also positive in the middle and negative for the outside. So the capacitance is 4 pi epsilon 0 AB over B minus A. Actually applying Gauss law here, something here. So you get similar results. For the A, it will be 4 pi R squared. And you substitute here an integration and you get this. It is something like 1 over A minus 1 over B, something like that. So it should be easy. And for the lower case, it is maybe more useful. I'm not sure, because I'm going to use them. Yeah, actually, so for the lower case, we assume that A is equal to R and B is tends to infinity, which means that we don't have the outer sphere, because making two spheres with the same center is not trivial. So we only make one inside. So if B tends to infinity and A is finite, so B minus A is B, and the B minus A and B can be cancelled. So A substitute into R, so we get 4 pi epsilon 0 R. So that is a capacitance of an isolated sphere with a radius R. So it is only related to the geometric size. Actually, when I learned electromagnetism, I don't really know why we need to calculate this, but actually, when you really need to buy one from the market, actually, they decide following some sort of this equation to design the products. So they can make different capacitance, resistance, something like that. So for the checkpoint 2, well, it's not important, so I just skip it. Okay, for this one, Okay, for this one, oh, I just have this thought, but no problem. So for this one, we have a battery here, which is 12 volt, and we have a switch. We have a capacitance C equals to 0.25 microfarad. Yeah, the SI unit is farad. So we have a capacitance, we have a simple battery, switch, and capacitor. So the size is L 0.5 centimeter, and the phase the area is A, and it consists of copper. And actually, the density of the conduction electron is n, small n. So it asks you what's the depth. The depth within the plate must electron move to the plate face as the capacitor becomes charged. Okay, first of all, we would like to calculate is the charge on this capacitor. So Q equals to CV, no problem. 0.25 times 10 to minus 6 times 12. So it will be nothing but 3 times 10 to minus 6 Coulomb. Okay, better looking at the PowerPoint. The resolution of the PowerPoint is too low. So this is easy, and then as we know, the density of the electron is this one. So we try to calculate. Not yet. We want to calculate. How many electrons for this charge, which is actually n equals to 3 times 10 to minus 6 over 1.6 times 10 to minus 19, which is the charge for a single electron. So it is something like this, 10 to 13 electron. Actually, we want to calculate the depth because, as we know, there will be charge here. Sorry. So we have positive charge on the top plate and negative charge on the bottom plate, right? And it tells you that the electron has a density n, something like that, because the electron needs to occupy some area, need to occupy some space. They cannot smash into a single point, right? So it tells you the density of the electron can be like that. So we need to know, according to that density, how much space you need to occupy. Oh. Okay. So of course, we have the density. So n should be equals to the density times the space, of course, the area times the width. This is the width, or you can say the height the electron need to occupy, and the surface area is A. So the total space is A times B times the density to be the total number of electrons, right? So we get D equals to N over AN. So we plug in all the values. So the answer will be 1.1 times 10 to minus 12 meter, which is 1.1 picometer. Because the charge will be positive Q will be on the top plate and negative Q will be on the bottom plate. So actually calculate the bottom part. Due to the free electron can move to that part, and actually for the top plate, some free electron move away from that to the battery. Okay. Any questions? But I believe it is for the bottom plate. The top plate would be a different value, but it doesn't. Well, it is arguable, but I don't think the density for the top plate will be the same, because this is the electron. For the top part is the nuclear. For the top part is due to the free electron move away, so it has positive charge. So for this parallel capacitor, we just add all of them together. Done. For the series capacitor, we have the inverse, sum them together, and inverse again. Done. So we have a 10 minutes break.